So what we did yesterday was we were estimating population means when we had a value for the population standard deviation. And the question I want to start off asking you is, if you don't know the population mean, what's the chances you're going to know the population standard deviation? Slim to none. Because if you had the information for the population standard deviation, why in the world would you not then know the mean? Now there are going to be cases where you might have a really, really good idea of what the population standard deviation is. It could be that somebody did the same experiment that you're looking at. They're trying to find the population mean 5 years ago. And so they actually had a reasonable estimate of that population mean because they had access to the whole population. So they were collecting information and they had census data, which is from the whole population. So in that case, they might know what the population standard deviation was then. And it would not be unreasonable to assume that population standard deviation, unless there's something that would have changed about that population, it probably hasn't changed. But the mean might have changed. So there might be, from a previous study or a previous census, there might be some information known about a past population. So you might have a good estimate of it, so then you can use that estimate. But most of the time we don't know what population standard deviation is. That's just the way it is. So in order to use the normal distribution to find confidence intervals for the mean, you need to know the value of sigma. And if we don't know sigma, what we do, if you remember from yesterday, I said the best estimate for the population standard deviation is the standard deviation of the sample. So we can use the sample standard deviation S to approximate sigma. But because we are estimating a population mean, we're allowed to use a sample mean as a free guess for what the population mean might be. But if we have to also guess at what the standard deviation is, we lose what's called a degree of freedom. If we have to use two estimates for one single problem, we lose what's called a degree of freedom. That degree of freedom might not mean much if the sample's pretty huge. But it will mean a lot if the sample size that we have is smaller than 30. It can make quite a bit of difference. So what we're going to do is we're going to use another normal type of distribution, but we're going to use a distribution that's called the student T distribution. Not student as in you are students, but because the guy that actually did the research and established the student T distribution used the pen name student to publish his research. So this is how a T distribution is going to work. A T distribution is bell-shaped. And it's symmetrical about the mean. So far that sounds like a Z distribution and your standard normal distribution, right? Skipping over the second requirement, the total area under the curve equals 1, just like with a normal distribution. The mean, median, and mode are all at 0, just like a normal distribution. But the degrees of freedom is the size of the sample minus 1. The minus 1 is for that second guess that we're making, that second estimate. And as the degrees of freedom increase, the actual shape of the T distribution approaches the standard normal distribution. So if you've got a large sample, like 100, you have 99 degrees of freedom. But your T distribution isn't going to look much different from your Z distribution. It's going to be pretty close to the same. If you have a sample of 50, it's not going to be quite as close, but it's still going to be really close because you'll have 49 degrees of freedom. If you have a sample of 25, it's spread out a little bit more than a z-distribution. And most of the t-distribution for 25 degrees of freedom isn't going to fit within 3 standard deviations. It might be that 99.7% of your t-distribution for a sample of 25 might go from -4 to +4 instead of -3 to +3. And if the sample size was 10, then it might be even more than that, more spread out than that. But other than that, the confidence interval for estimating a population mean when sigma is not known isn't much different. Instead of using z alpha over 2, we're going to use something called t alpha over 2. And we're going to replace sigma with s and turn it into the standard error by taking s and dividing by the square root of n. And then once we've calculated that margin of error, we're going to subtract 1 margin of error from the sample mean. And we're going to add 1 margin of error to the sample mean. And that's going to give us the confidence interval for the mean with whatever value of t we have for that sample size and that level of confidence. And I think I've missed a slide there, so I've got the problem statement up here. So this is the problem that we're going to do. And the only thing that's going to be different about the way that we're going to do this problem and the way that we did yesterday's problems is that we're not going to be able to answer the question, what is the value of sigma? So I'll have the calculator handy and we'll work this problem and you'll see how it's alike and how it's different. So this problem is a test of the Atkins weight loss program, and it says you have 40 individuals participated in a randomized trial with overweight adults, and after 12 months the mean weight loss for that sample was found to be 2.1 pounds and a standard deviation of 4.8 pounds. So our first question is, what's the best point estimate of the mean weight loss of all the overweight adults who followed the Atkins program? Remember that your point estimate, since it's for the mean, and the mean here is we're estimating mu, our best point estimate is your sample standard deviation. So your point estimate is always the statistic that corresponds to the parameter that you're trying to estimate. So then they say construct a 99% confidence interval estimate for the mean weight loss of all such subjects. Well, here's how we're going to do that. We're going to get the calculator. And very similar to what we did yesterday, we're going to press the stat button and go over to the test menu. And the only thing that we've seen so far is the z-interval. But if we open the z-interval, the very first question it asks us after the fact that, you know, do you have statistics or do you actually have the data? The first question it asks us is, what's the population standard deviation? Well, we don't know that. And that kind of stops us dead in our tracks. So because we don't know the population standard deviation, then we're going to go back to that stat menu and see if there's maybe another option. And there is. Option 8 says t-interval, and that's the t-distribution. So we choose the t-interval, and the reason that we choose the t-interval is because notice on this screen it doesn't ask us the value of the population standard deviation. It only asks us for sample information, so we're good to go. So given that, it says, okay, what is the mean? Well, if you read your problem statement, what's the mean? 2.1. And then it says, okay, what's the sample standard deviation? Well, that's 4.8. And then it asks you, what is the sample size? That's so that it knows how to go get the appropriate t-distribution, because there's one for every single sample size under the sun. And it's calculated with a formula, and we don't want to use t-tables, even though you could use something called a paper t-table. We don't want to use t-tables because the t-table formula, I mean, we'd have to have an infinite number of pages because you could have all kinds of sample sizes. So for the sample size, we tell it the sample size is 40, and it'll go calculate it for us, rather than us having to look up a value on some kind of a table or something. And then the next thing it asks us is the same thing it would have asked us for any other problem we work in this chapter. It says, what level of confidence do you need to have? And that's going to be 99%. So what we're doing here today is really no different from what we did yesterday, except that we didn't have a population standard deviation. We have a sample standard deviation. And because we have a sample standard deviation, we're going to use a t-interval instead of a z-interval.
Do we always use 0.99?
For 99% confidence, yes, you have to read your problem, and it says here construct a 99% confidence interval. It's not always 99. Anybody else have a question? Okay. So then we go down to calculate and hit enter. And faster than we could do any kind of math, if we had to do the math, we know the answer. Yes, ma'am.
So does it always give you a confidence level that it wants you to use?
You have to, because otherwise you won't know which one to construct. So they'll have to give you the confidence level. They'll have to give you sample information. They may give you population standard deviation, but they might not. Okay? So the answer to our question here, when we say construct a 99% confidence interval, using what we've got here, if we write it out in probability notation, this is what we write. The probability that the mean of the population is between 0.04484 and 4.1552 is 99%. That's what it means in probability notation. Now, that's not necessarily what you're going to write in conclusion of the question for a problem. We want to say what that means. So what we say what that means is we are 99% confident or certain that the mean of the weight loss for all individuals who participate in the Atkins weight loss program. Is between about 0.04 and 4.2, or let's say 4.16 pounds. After 12 months. So that's the actual response to the question. If you're asked to interpret that interval or explain that interval, then you have to actually write all of that out. And there's your confidence level statement. Now let's stop and talk just a second about practicality here. Does anybody know anything about the Atkins weight loss program? It's basically low carb, somewhat low fat, high protein. So you eat lots of meat, you eat no sugar, you eat a lot of high fiber vegetables, but you don't eat any sugar, you don't drink milk, there's all kinds of carbs you can't have, you don't eat bread. And you're supposed to lose weight because it's supposed to make your metabolism boost up into high gear and basically have to burn all your fat cells. Now the question for me is, thinking about what you're actually eating on that program, you're eating a lot of meat. And I know people that have been on the diet, they eat as much as a pound of meat at a meal. That's a lot of meat. And they can only eat vegetables like salad and broccoli, and they can't eat like carrots and potatoes. They have to eat things that are basically really high. And it's not bad for you, vegetables. The vegetables are good for you. But, you know, it's a lot of meat, and a lot of the times, you know, they stay on that diet and they lose weight. But if this is actually the result of being on that diet for 12 months, do you think that diet's worth it? Why? Because how much weight are you likely to lose? Over 12 months, over a year.
Less than 5 pounds.
Less than 5 pounds. You're going to go through all that, and at the end of the year, you've lost less than 5 pounds. So based on this is the practical side of confidence intervals. Based on the evidence that we gained here, if somebody were to say, is the Atkins weight loss program effective based upon what we see here, our answer would be, well, no. You know, you think 5 pounds is all you need to lose, then, you know, you probably lose 5 pounds if you just exercise a little bit more. Okay? So there is a practical side to this. So here's our next question. In a test for the effectiveness of garlic for lowering cholesterol, 49 subjects were treated with raw garlic. Well, I bet they didn't have a lot of friends wanting to be hanging out with them in close quarters. Their cholesterol levels were measured before and after the treatment, and the changes, which are before minus after, in their levels of LDL cholesterol, which is the bad cholesterol, had a mean of 0.4 and a standard deviation of 21.0. What's the best point estimate for the population mean net change in LDL cholesterol after the raw garlic treatment? Well, always the best point estimate for the population mean is going to be the sample mean. Here's your sample mean. Okay? Construct a 98% confidence interval estimate of the mean net change in LDL cholesterol after the raw garlic treatment. Okay, in addition to the sample mean, we also have the sample standard deviation. We're going to need that. because
the
we're gonna
problems
use
are
that.
different.
Yeah,
I think the problem you're doing is different than what we have.
The numbers are different.
Yeah,
for
the numbers aren't the same.
Okay, well, let's change to the numbers that you have. You tell me what your numbers are, because I may have pulled from the wrong slide. What are your numbers?
3.2.
For X bar?
Yes.
Okay.
The sample size is 47.
3.
Okay. And is the standard deviation different?
Yeah.
18.6.
I'll make a note to change that in PowerPoint.
And we're only supposed to construct a 90%
How,
confidence.
how much?
90.
90%? Okay, so we'll make those changes so that it'll all match up. So here's what we changed. This is to help me remember to change it. And I'll go back to my office and change that before my next class. Okay, so given those numbers, we're going to construct a 90% confidence interval estimate for the net change in LDL cholesterol after they ate all this raw garlic. So here's the sample information we have. And our confidence level in this case is going to be 0.9 or 0.90. Move that up so you can see all that. So we'll get our calculator, and again, we don't see anywhere in this problem that they gave us the value of the population standard deviation. All we have is sample information. So anytime all you have is sample information, anytime, then you're going to go stat and over to your test menu and not choose number 7. Whoops, one more. Not choose number 7, but choose number 8. And then you just answer the questions. So we're going to let it calculate the interval for us. And once it calculates the interval, we're going to write it in probability notation. Oops, that was not good. I'll sit tight for a second. I accidentally turned off the projector. Okay, there we go. So we're going to find two numbers. That we are 90% sure that the actual change in their cholesterol levels fell. So all we got to do is hit calculate, and in no time at all, it comes back and says that interval is from negative 1.354 to positive 7.75. 44. And one thing to always check when you do this is make sure that since it repeats back to you what the mean and standard deviation and sample size were, make sure it matches what you thought you put in. Because it's easy to transpose two numbers, so make sure that matches before you actually write your answer down. Because it's kind of hard to mess up the procedure as long as you put in the right numbers. Just, double check your numbers. And it says that the actual change is between negative, and a negative change means their cholesterol actually went up by as much as 1.354 microliters. And then positive 7.75, which is actually, maybe that's a pretty good change. But now here where it says interpret your interval. What number do you know is between negative 1.354 and positive 7.7544? What very important number is in between those two?
0.
0. And what does 0 mean about the actual change in your cholesterol level?
No change at all.
No change at all. So here, you drove away the vampires, but you also drove away all your friends, and your cholesterol didn't change. So when it says interpret your interval,
Isn't it just, I'm pretty sure it's just 90%.
yes, it's 90. And we don't need the calculator for this, so let me get it out of the way. The bottom line, the treatment was not effective. Because essentially, 0 is within the confidence interval, which means there was no change due to the treatment. Okay? Now this is the way they actually conduct these types of studies. And if they got on television or went in a magazine and said, this treatment works, and you look and read their statistics, well, no, they're lying. Their treatment did not work. Yes, ma'am?
Where you say like the probability is mu is between the two numbers, do you ever say it's less than or equal to, or is it always just less than?
It's always just less than.
Okay.
It doesn't matter if it's less than or equal to, because on the normal curve, because it's continuous, it doesn't matter if you include your boundaries or not. You could say less than or equal to. It wouldn't hurt. Doesn't hurt or change anything.
Okay.
Okay?
Thank you.
So hopefully by this point in the course, you're starting to see that there might actually be some practical use in what you're learning here. And one of the reasons that you take this course is to make you a better consumer. Now the last kind of problem that we're going to look at is going to be about population proportions. We've done problems with sample means, okay? Using sample means to estimate the population mean mu. We've done it when we knew the population standard deviation. We've done it when we don't know the population standard deviation. But the last thing that we talked about on the first lesson, the very first thing we said was that there is a point estimate for a population proportion. If you're trying to estimate the percentage of a population that has some particular characteristic. You usually see these kinds of problems a lot around election time, because people start reporting, if the election were held today, then this percentage of voters would vote for this candidate with a margin of error of plus or minus this many percentage points. Okay? And a lot of times, even today, this is the one you'll see the most in the news. This is the application that you'll see the most in the news. There are formulas. You're not going to need the formulas, but there are formulas. For example, our first one says your margin of error. You know what that is. That's the part you add to the center and you subtract from the center to get your upper and lower confidence levels. So the margin of error formula is based on a z-score. It's based on a z-score because this whole area of probability and confidence levels is based on a binomial distribution, because if you think about the election, either the the person voted for that candidate or they did not. Even if there's 5 candidates running, they either voted for that particular candidate or they didn't. So it's a two-choice situation. So it's kind of related to the binomial, which means you're going to have a population proportion you're going to want to estimate, but you're going to need to use a sample proportion to do the estimating. And if you're using a sample, you're going to know the sample size. And if you use the sample, if you know the proportion of the sample that did vote for that candidate, you also know the proportion that didn't. So your confidence interval is kind of like what we did before. You take your actual population proportion, which you'd like to know, and you estimate it by subtracting a margin of error from the sample proportion and adding a margin of error to the sample proportion to get your confidence interval. So it's the same process, but now it's going to be for percentages. And because it's for percentages, you always want to round your confidence interval limits to 3 decimal places, so that when you change it into a percentage, it doesn't come out to be 33%. It comes out to be 33 point something percent. Okay? Or whatever percentage it is. So here's our first example. An important issue facing Americans is the large number of medical malpractice lawsuits and the expenses that they generate. Because those malpractice lawsuits generate expenses not just for the people involved, but for taxpayers, because the taxpayers are paying the judges, the taxpayers are paying for the court time it takes, and then the people are paying for the lawyers, the people that bring the suits, but the malpractice insurance paid for by the doctors and the hospitals is costing people that go to the doctors and hospitals more because they have to recoup that cost somewhere. So it basically is expensive for all of us if these people are filing these lawsuits what is called frivolously. They really, they're just in it to see if they can get some money, and they know they really don't have a case, but it winds up costing everybody a bunch of money. So what happened is, in a study of 1,228 randomly selected medical malpractice lawsuits, it was found that 856 of them were later either dropped or dismissed. And what that means, if they were dropped or dismissed, either the people realized they weren't going to get any money out of it after they've already spent money and cost everybody money, or there was no evidence to support their case. So the question we have here is, what's the best point estimate of the proportion of medical malpractice lawsuits that are dropped or dismissed? In other words, what we're trying to estimate is P for the whole population of all lawsuits, all medical malpractice lawsuits. But the only information we have comes from this sample. And in the sample, they had 1,228 people. And out of that 1,228 people, 856 of them were dropped. That's enough information to actually calculate P hat. Because if you remember from back in chapter 5, P hat is equal to X over N. The number that were successful, dropped in this case, out of the whole entire group. So P hat in our problem is going to be 856 divided by 1,228. And it's that big old long decimal number, but you don't necessarily have to write that big long decimal number down. What you want to do is you want to say the best estimate is P hat equals 856 over 1,228. But it is interesting to note that 0.697 or 69.7% of those lawsuits in that study were dropped or dismissed. So then the next question that we have is construct a 99% confidence interval estimate of the proportion of medical malpractice lawsuits that are dropped or dismissed. So what we're finding is the probability that the actual population proportion is between these two numbers, or these two percentages, is going to be 0.99 or 99%. Okay? And then we're going to interpret that and then answer the question at the bottom. So with the calculator, because we do all of these on the calculator, we don't have to actually calculate anything. We're going to go to your stat button and go over to tests. And we don't want to do a z-interval because a z-interval is for mu. It's for a population mean. This is not a population mean. This is for a population proportion. As soon as you see that word proportion, or it says best estimate for the percentage of, proportion and percentage mean the same thing. We're not talking about a mean, we're talking about a proportion. So you can't use z-interval. You can't use t-interval because both of those are for population means. We don't have two samples, so it's neither one of those two. So we're going to have to go all the way down to option A. We're going to go down to option A. And option A is a 1 proportion. A 1 proportion z-interval. That word proportion or percentage tells you what to choose. Okay? And then it asks you some questions, just like it does on the others. First one says, what's the value of X? Now, X would be the ones that were dropped or dismissed. So that's 856. Then it says, okay, how big was the total sample? Well, that's 1,228. And then the last question is the same one that we're used to being asked. What's your level of confidence? And that's 99%. So that's 0.99. And when we hit enter, it's going to actually calculate these two numbers for us. Okay? It's going to calculate those numbers for us. So those two numbers are 0.66329 And since it said round to 3 decimals, then I rounded it off to 3 decimals. And 0.7308 would be 0.731. And notice here again, it repeats some of the information back to us. It doesn't give us X, but it gives us a sample size. And it also gives you p hat as a decimal. Okay? It also gives you p hat as a decimal. So what that means is that we're 99% sure that between 66.3% and 73.1% of all of these lawsuits get dropped or dismissed. We're 99% sure that the actual population proportion for the lawsuits that get dropped or dismissed is between 0.663 and 0.731. So then we have our last question, and this is one that we need to think about, just like the one we did before. It says, does it appear the majority of such lawsuits are dropped or dismissed? Now the majority is 50% or more. Okay, our confidence interval says that even the lower end of the interval is above 50%. 50% is not within that interval. So for that reason, we say, yes, it does appear. Yes, it does appear that the majority of all such lawsuits are dropped or dismissed because 0.5 is not within that interval. It's below the lowest end of that interval. Okay? Any questions? One more example. In USA Today survey, 20.8% of all of the 144 respondents said that they wanted to have their boss's job. What's the best point estimate of all the workers, according to that survey, that said that they'd like to have their boss's job?
20%.
So, sample proportion of 20.8%. That's the best estimate of P. So then they asked us to construct a 95% confidence interval estimate of the proportion of all workers who aspire to have their boss's job. Now, in other words, what we're going to do is we need some information. We know that we have a 95% confidence level. We know that we have 144 respondents. But then when we get to putting the information in at A, 1 prop, Z interval, and again, it's proportion, 1 proportion, because it is a estimate of the population proportion, of the percentage of the population said that they'd like to have their boss's job. The problem is we don't know what X is. Yes?
I don't have this one.
Yeah.
None of y'all have this one? Do you have another problem that's similar?
We have the next one, the Pew Research one.
Okay. Well, let's go ahead and finish this one anyway, just to make sure that you understand something. So don't worry about taking notes, just watch. If we have this problem to do, and we're going to go over here on the calculator, because there is a good piece of information in this that might be useful in the next one. Since we're going to go here, the first question it asks us is what's X? How can we use what we've got to figure out what X is?
No. 0.208 times 144.
Right. We know the proportion of the 144 people is 20.8%, so we could put, and you don't even have to do this as a separate calculation. X is going to be, change that percentage to a decimal, because it does need to be a decimal. So that's going to be 0.208 times the sample size, which is 144. And you don't even have to do it somewhere else. You can sit right there on the calculator on that screen and type that multiplication in, and when you hit enter, it changes it to 29.95. Okay? But can we actually use 29.95? What do we always have to do when we're talking about choosing something? You're going to have to round it up to the next whole number, because you can't take 0.952 of a person. You have to take the whole person. So even though it turns out to be, 29.952, you know that you need to round up to 30. That value actually needs to be 30. So move your cursor back up there and change that to 30. Even though it came out that way, you just saved having to do some extra arithmetic somewhere else. You've got the answer right there, and then go ahead and round your answer up to 30, and then put in your correct sample size. And our confidence level is only 0.95. And you can see why P hat would have been 0.208, because that would have been rounded to 0.208 with that string of 3s after it. So your confidence interval is from 0.142 is less than the population proportion is less than 0.274. Since that's 6, we'll call that 5. Is equal to 0.95. So we're 95% sure that between 14.2% and 27.5% of all people, according to that survey, would like to have their boss's job. That's the interpretation of that. I'm going to slide back down here for a second and ask you. And we're actually at this moment we're reviewing for the exam, because this has nothing to do with Chapter 7. In a USA Today survey, 20.8% of 144 respondents. Would you trust that survey? Would you trust the results of that survey? Why not, Ethan?
Not enough people.
Okay, number one, it's not enough people. Because if we're talking about 144 respondents, and we're talking about all the workers in the United States, 144 144 is not very many. Now, I might trust it more if it was a survey that was conducted by Gallup polls or AP polls or Pew Research or some kind of reputable research firm. It's not that I don't trust USA Today, but how do you suppose they got that information?
Self-reported.
That's right. They probably either did an internet survey or they put a link to a survey in their newspaper and asked people to click on the link and, you know, say whether or not they did. So the people that responded were voluntary response. So those were actually probably mostly people that either really wanted their boss's job or really didn't. Okay? And there's a lot of people in the world that really don't want their boss's job. I'm one of them. I had my boss's job. I don't like my boss's job. I'd rather do what I do. Okay? So always be thinking about that. I don't want you to forget that, you know, that way back in chapter 1, we learned a lot of good stuff. Don't forget about that stuff. That stuff's still with us. And that's why I wanted to go ahead and complete this problem even though it's not in your notes. In fact, I'm going to make a note here that when I do this again, I need to add this to the notes. Because I think that was why I put it in PowerPoint. Okay, so here's the one that we've got. You've got this in your notes. It says Pew Research Center poll 745, and notice here, remember what I was just telling you. $745 randomly selected adults. This is a random sample. That survey was not necessarily a random sample in the last one. The other thing to notice here is there's a number of reputable polling agencies. The Pew Research Center is one of them. So is AP polls and Gallup polls and a few others. Pew Research Center, besides doing research, the Pew Foundation actually funds public television. This is a good size sample, even though it's not, you know, a lot more than the last time. It's a pretty good size sample, especially if it was randomly selected, because I'm sure they used a method to select that 745 that made sure that that was a good random sample. They used a random probability method. So this is probably pretty reliable, and 79%, which is your value of p hat, said that it's morally wrong to not report all your income on your income tax returns. So the best point estimate for the proportion of adults, because again this is a proportion problem, need to focus on that PROP, that feel it's morally wrong to not report all your income on your income tax returns. That proportion estimate is that p hat is your best estimate of p, and p hat is 0.79. We also know that n is equal to 745. And we want to construct a 95% confidence interval. So we know that C is equal to 0.95. So we're going to construct the interval and then we're going to interpret the interval. I'm going to get my calculator. I'm going to go back to the same place we were. I do a 1 prop z interval. And I'm going to show you here, I'm going to kind of model for you how I want you to show your work on this, because you do need to show your work. So on showing your work, I would want to see which screen you were on. I want to know what you think X is. I want to know what you used for N. I want to know what you used for C, and then I want this. Okay? So when we put that information in the calculator, he had his 0.79, but it doesn't tell us the value of X. So just like in the last problem we did, the way that we do this then is put in 0.79 times the sample size, which was 745. But when we hit enter, once again, we don't get a whole number. So we're going to round that decimal number to 589. That's what we're actually going to use for that, is going to be 589. And 0.95 is fine. And then we hit calculate. And once we hit calculate, then we can fill in our interval. So 0.761 and 0.8198 would actually round to 0.820. You want to be sure you round correctly. So then when we interpret the interval, we will say I'm 95% certain that between 76.1% and 82.0% of all adults think it's morally wrong to not report all your income on your tax returns. Okay? You always want to interpret your interval, not just write it. Any questions? Okay. I'm going to give you all a choice here. We have one more kind of problem to do. And that's the sample size problem. Remember when we were doing problems for the mean, we had to sometimes be able to determine how big a sample we needed before we started conducting our study. We're going to have to find sample size here too. We can take a break and then come back and we will do this problem. But the couple of problems we have here, we're gonna get done by 12 o'clock. If we don't take a break. If we do take a break, then we're not gonna get done until about 10 or 15 after. Do you want a break, or do you want to go ahead and do this problem and get out early? I'm gonna leave it up to you.
Go ahead and do it.
Yeah.
Who wants a break? Okay, we're gonna go ahead and finish, let you go early. I like to always give you a choice when we're this close to the end of class. Okay, just like before, when we had sample means, we sometimes need to find a sample size. We had a formula for sample size. Remember, the calculator does not do this for you. You're stuck, you've got to do it for yourself. Remember that this is for proportions. So you're going to have to read your problem carefully and look for the fact that the problem is about proportions, not means. Actively look for the word mean or proportion, because that tells you which way to go on your problem. When an estimate of p hat is known, in other words, when they give you some kind of previous information. 6 months ago we conducted a study, and at that time the proportion of the sample that said whatever was this. Okay, that's an estimate. So they may tell you an estimate of p hat. If you don't have an estimate of p hat, if it's not given to you in the problem, then your safest estimate of p hat, because I don't want you to think this is magic. Your best bet is that p hat equals 0.5. Just like shooting an arrow at a target, you shoot for the middle because you want to hit the bullseye. Your best guess is always going to be right dead center of the middle probability, 50-50. There's a 50-50 chance. And what this 0.25 comes from, so it's not magic, is using p hat times q hat when p hat is 0.5 and q hat is 0.5, and 0.5 times 0.5 gives you 0.25. So that formula is not magic. It's just based on thinking that p hat is unknown, therefore your best guess is 0.5. Okay? I will give you these formulas on the test. You do not have to memorize them. That's not necessary. I will give you a formula sheet. You don't have to have that. The only caution I'm going to make here is the same caution I made before. When you're talking about finding a sample size, you can't take 0.28 of a person. Okay? You have to take the whole person. So you're always going to have to, just like when we did class width way back in chapter 2, just like class width, you have to round sample size up. You always round up. 32.2, you need 33. That's important. So here's our problem. You're the operations manager for American Airlines, and you're considering a higher fare for passengers in the aisle seats. If you've ever flown, there's a real good reason you want to be in the aisle seat. Those are the safest seats in the plane. You don't want to be sitting in the very front. Business class usually gets conked if the plane goes down. And you also don't want to be sitting in the tail of the plane and a window seat. You want to be sitting down in the middle of the plane so you've got lots of plane around you in case it goes down. Okay? You want to estimate the percentage of passengers that prefer, my little airplanes in the wrong place, but that now prefer the aisle seats. How many passengers do you need to survey if you want to be 95% sure of your answer So let's be paying attention to the information we're given here. You want to be 95% confident. And you want to be within, and what did I tell you that word within tells you? Within means they just told you the margin of error. And since it's 2.5 percentage points, you need to be able to change that to a decimal to be able to use it. Okay? Our question is, what is the value of n? We need to find n. How many randomly selected passengers? Our first part of the problem says, assume nothing is known about the percentage of passengers that prefer aisle seats. Nothing is known means you have no estimate for p hat. You don't know. You have no estimate for p hat. If p hat's not known, use p hat equals 0.5. That's your best guess, always. Then you don't really need that second formula, even though I'll give it to you, because your formula says you take p hat times q hat and you multiply it by z alpha over 2 divided by your margin of error. And then you square what's in the parentheses. You don't square p hat and q hat. You only square what's in the parentheses. So if we plug in what we know, p hat is 0.5. If p hat is 0.5, what's q hat?
0.5.
0.5, because it's 1 minus p hat. Okay? Then inside the parentheses, we're straight out given the value for E. We're not straight out given the value for Z alpha over 2, but what we are given is that C is 95%. So in order to find Z alpha over 2, 1 minus C is 0.05. That's actually alpha. Okay, that's the value of alpha. And then alpha over 2 is 0.025. So Z 0.025 is the area under the curve is 0.025 to the left of that Z value. Okay? This tells you it's the Z value that cuts off 0.025 in the bottom end of the curve. And the mean of z-scores is 0 and the standard deviation is 1. And then you use your calculator to figure out what z alpha over 2 is. So this is going back to chapter 6 again. Second, distributions, inverse norm, 0.025, comma, 0, comma, 1. Close your parentheses, hit enter, and your value of z is negative 1.959, which is 1.96. And it doesn't matter if it's positive or it's negative, because when we get done doing the arithmetic, we're going to square it anyway, and when we square it, the answer is going to be positive. So I'm going to take that number, plug it in the formula, and now we're going to do the formula. And the answer comes out to be 1,536.64. So your sample is going to need to be 1,537. Okay? Questions? Got to be able to find everything. Now, what does the next one ask you that's different? What do they give you in the next one that's different? You tell me.
They give you p-hat.
They give you a different number for p-hat. You have a different value. You have p-hat is known. Okay? Assume that a recent survey suggests that about 38% of pastures prefer the aisle seat. Okay? About 38%. You've gone from having no estimate of p-hat to having a value for p-hat. If p-hat is 0.38, what's q-hat? Okay, it's 1 minus, so that's 62. Nothing else changed. Your confidence level is still 95%, so your z-score is still plus or minus 1.96. That didn't change. Because the confidence level is the same, z alpha over 2 didn't change, because z alpha over 2 is tied to your confidence level. Your margin of error didn't change. So what's changed in your formula is just the value of p-hat and q-hat. So we can do the exact same calculation all over again, except we need to change the value of p-hat and q-hat. So I changed both of those, nothing else changed. And my sample size went down. When you have an estimate for p hat, you have more evidence, so you don't need as big a sample. You already have some previous information, so you don't need as big a sample. So this gives you the maximum possible sample size when you don't have an estimate for p hat. Now our estimate's smaller because we have an estimate for p hat. And despite the fact that that's 1448.12, we still need to round up. So you need 1,449 people. Okay? Anybody have questions? If not, I do have one that I want you to try. If you will do that one as a post and show me and tell me what you got, I'll give you bonus points on your test.
Which number?
This is the one at the end of your notes that says you try one. So I'm not going to do this one. I want you to try this one. The one that I'm going to do, we've not done one like this. So I want to do one like this with you. We did not do an example like this, and it'll take just a couple of minutes to do it. This is a problem from data. We don't have statistics, we have the data. So reading the problem, it says in a sample of 7 cars, each car was tested for nitrogen oxygen emissions in grams per mile, and the following results were obtained, and this is based on data from the EPA. And it says, assuming this sample is representative of the cars in use, construct a 98% confidence interval estimate of the mean. Okay, mean. This is for the mean. Tell me what we've got. We've got data. Can we calculate the sample mean?
Yeah, put it in a list.
Yeah, we're going to put it in a list. Does this problem tell us anywhere in here what the value of the population standard deviation is? Is sigma known? Yes or no?
Yeah.
No. We see no other numbers in there except sample numbers. That tells us that our choice between Z and T interval means we're going to have to use a T interval. This is our confidence level. So this is how we're going to do the problem. We're going to get the calculator. We're going to hit the stat button, go to the edit screen. I don't care what's in list 2, I don't need list 2. I just need to put data in list 1, so I cleaned it out. My data is 0.06, 0.11, 0.16, 0.15, 0.14, 0.08, 0.15. Make sure that you put the right numbers in. Then we hit stat again. We right arrow over to tests. Z interval is for means, but we don't know sigma, so we can't use it. We need T interval. Hit enter. We don't have stats, so we tell it we have data. If your list doesn't say list 1, make it say list 1, because that's where you put your data, unless you put it somewhere else. If you put it in list 5, then put list 5, whichever list you put it in. The frequency in these problems is going to be 1 unless you've got a frequency distribution. I don't plan on giving you a frequency distribution on the test or quiz. Your confidence level is 98%. Make sure you get the confidence level right. Write all of that down. That is as important as anything else you do. Write down what you put in that calculator. Then calculate, you can tell me about the answer. Paper's wiggling around. Oh, I left out a 0. Sorry. Always put your interpretation back in terms of the problem. So we're 98% sure that the mean emissions of all of these kinds of cars is between 0.07521 and 0.16765. You can round off, just don't round off to just one decimal, round off reasonably. And go ahead and write your sentence. Okay? And unless y'all have questions, we're done.
The problem that you wanted us to do, where in Shelby do we see?
I'm going to put a folder up and show you that, and I'll actually post that one problem.
Okay.
Okay? Okay, test is when? We don't have class on Thursday.
Oh, Wednesday.
Test is when?
Monday.
Monday, because I don't want to start a new chapter until we actually test over this one. Okay? I will put up a practice test to help you. And I will post the answers to the practice test.